mean, I can do that. I guess I can do that. I should do that from the main device, okay? Is that okay? Okay. I mean, this is not trivial. I mean, starting from the function of one variable and from the straight line is not trivial at all, because I'm just showing what really matters for the next part. I guess this is called, actually this is material from what is called precalculus. I guess that all of you are familiar with the concept of function of one variable. Look at this equation. What is the difference with this one? Is that the x variable is not x, it is x underlined. And this means that independent variable can be independent variables. We may have more than one independent variables, but in general, at least in our models, there will be only one dependent variable, okay? For instance, x can be a vector of two variables, x1, x2. In this case, I would have y is a function of x1 and x2. For instance, the demand is a function of the income and the price of the good, two variables. X in general is a vector, so it is an ordered list of entries. In general, we may have n independent variables, okay? So this is the representation of a vector. In particular, this is a column vector. In other cases, we may have the same entries in a row, and this is called row vector. And of course, also the structure matters with vectors. So what is a function? A function basically is a rule to obtain output y from input x, where x can be a multivariable vector. That is, x is the input, f is a certain number of operations on this input in a certain sequence. For instance, take the square root and then add 3, and y is the result. Of course, in general, the independent variable is x, the dependent variable is y, but in many examples in our course, the independent variable will be denoted by t, just because it represents time. So in this case, f of t is just a graph, is the graph of a variable as depending on time, okay? Where time usually flows from 0 to positive values, up to plus infinity. Okay? This is an example. F of t is equal to 3 over 1 plus t, where t is a positive or non-negative variable at least, and this is its representation. It represents a quantity that starts now at the level 3, it declines over time, and it tends to 0. Okay, what is the domain? The domain of a function is denoted usually by d, and I can select any x, any value of the independent variable in the domain. This is the admissible set for the independent variable. Okay, I hope this is clear. These are other examples that, apart from being very important from modeling discounting in continuous time, they have a peculiar thing that must be explained. You see here, I have a function of time, again, v of t. It depends on t, but it depends also on another quantity, which is called I. This is because t is the variable, the independent variable, and I is a parameter. Okay? In fact, when I'm using this, I'm not studying a function, but a family of functions, one for each possible value of the parameter. Okay? And also this one is another example of a function that depends also on a parameter. By the way, these two parameters, I and delta, are two ways of modeling interest rates. One is the annual compounded interest rate, and delta is the logarithmic interest rate, or continuously compounded interest rate. This way of writing, of using discounting in continuous time, are very popular in economics. So we use this one much more than the first one. In financial mathematics and the bachelor degree courses, you may be familiar with this one, this way of representing discounting, but this one is most often used in modeling, economic modeling. What is the domain of a function? Is the set of all admissible input values for the variable x or the variables. What is the range of a function? This is a very important concept. The range of a function can be constructed in this way. We have the domain, D. Suppose that our variable is just x, not a vector, x. Take all possible values of x in the domain. Let x vary across the domain, fully across the domain. Keep track of all the values of y generated in this way by letting x vary in the domain, okay? The set of all possible values of y is called the range of f, okay? So this is the set of all possible output values when you let x range in the whole, over the whole domain. And also another important remark is that the rule f function is in general represented by a curve in the plane, but not all curves in the plane represent functions, okay? Only those by which there is a unique value y for any x in the domain. To show you an example, which is maybe not in the slides, but it is useful to see it. Okay, just to show you an example, this one is a function, and by the way, in this representation the domain is just this one, but the function may be defined also on the left of this point or on the right of this point, but sometimes the domain is not just the natural domain, it's the domain of interest for us, for the modeler. So we may be interested in this range. And this is actually a function. You see, take any value of x in the domain, and you see that you intersect the graph only once. And this means that there is only value for y corresponding to each x. Okay? But of course, this doesn't mean that the y, there is a unique y corresponding to each x, but the opposite may not be true, okay? Because in this case, for instance, this value for y corresponds to two different values for x, okay? To each x, for each x, there is only one y, but for a given value of y, there may be different values of x. But this is a function anyway. This is not a function. So this is the domain, for instance. But of course here there is a range of values for x that correspond to two different values for y. Okay? And this is not a function. It is. This is also important to. It is also important to stress this from the beginning. Okay? I mean, I could skip this, but just to show you an example of a natural domain. If I have the function y, or f of x is the function that is the rule. F of x is the square root of x. Of course, the domain is any non-negative value of x. The set of all possible admissible values for x. It is the natural domain in this case. What is the range of this function? The range of this function is 0 plus infinity. If I let x vary in its domain, I obtain exactly all the numbers, the real numbers included in this interval, okay, from 0 to plus infinity. Of course, the range, sometimes it is not so easy to see the range immediately. The range can be seen very clearly if you are able to study the function. Study the function, you have the graph of the function, and you realize what the range is. And it's very difficult to understand what the range is, a way to study the function like x divided by x squared minus 4. Here, what is the set of all at the denominator cannot become 0, so from plus minus 2, so this is the domain of this function. This is a union of, the domain is usually written as the union of intervals. In many cases, open intervals, okay? Do you all know what is the difference between an open interval and a closed interval, I guess? And a closed the basic definition is that an open interval doesn't include its boundary points. Whether a closed interval includes also the boundary points. So this is a closed interval on the left, you see, because it includes 0. There are other functions that have the same kind of domain, but 0 is not included. For instance, the log function, the logarithmic function. In this case, the domain would be open. In this case, it is closed on the left. This is considered a closed interval, okay? Okay, in this case, if one is able to plot the graph of the function, one can see that the range is minus infinity plus infinity. So the variable y ranges over the whole real line. This structure, f of x is equal to the log of x squared minus 4, is useful to illustrate the range and the domain, but it is also useful to illustrate what a function of a function is, or a composite function is, okay? A composite function means it must be regarded as a structure in our mind. So it's useful to regard a function as a composite function because some operations turn out to be easier in this case, okay? I can regard this as a composite function. There is a quantity, and then there is the log of this quantity. I will introduce the logs tomorrow. We should say something about the logs tomorrow. But this is the log of something, but something is itself a function of x. So I can regard this as an inner function and an outer function. The inner function is x squared minus 4. The outer function is log of something, okay? So log of g of x. Okay, so g of x is a parabola. It has the vertex on the vertical axis. If you here, g of x is this function. If you set x equal to 0, here you see that y is equal to minus 4. Then you know that this parabola is called convex or upward concave, just because the coefficient of the term of the quadratic term is positive, okay? And what is the domain of G is the whole real line. What is the range of G? If you let X range over the whole real line, you see that G has a minimum where it takes the value minus 4, and then it can take any other value from minus 4 to plus infinity. So the range is minus 4 plus infinity. Now, since the log of a quantity is defined only when this quantity is strictly positive, if you want to find the domain of f, not of g, of f, you must exclude the values by which x squared minus 4 is 0 or negative, okay? So the domain of f is from minus infinity to minus 2, union from 2 to plus infinity. So it is only this part here. Okay? Why? Because if you look at the value that this function takes here and here, but not here, you see that it takes values from 0 to plus infinity. Okay? You can see it here. And these values from 0 to plus infinity, which are the output of function g, are themselves the input of the outer function. Okay? So the range of the function f of x is from minus infinity to plus infinity, because this is a property of the log function. When the argument ranges between 0 and plus infinity, the log takes any value from minus infinity to plus infinity. So this is sometimes this is a useful structure to look at to understand the behavior of functions. Okay, not just in this case, but I mean to compute derivatives. The rule of differentiation, computing derivatives of composite functions, since there is an outer function and an inner function, can be done step by step, okay, in 2 different steps. And this is called chain rule, or rule for differentiation of composite functions. Sometimes this is another example that shows the distinction between the natural domain and the domain imposed by the modeler. For instance, the log of x is a function, is the blue function here. I will show you the properties of the log function tomorrow. Sometimes we may have the log not just of x, but 1 plus x, for instance. So the independent variable has increased by 1 unit. We can understand the behavior of this new function just moving the graph to the left by 1 unit. And this means that this function is defined from minus 1 to plus infinity instead from 0 to plus infinity, okay? So the natural domain of log of 1 plus x would be from minus 1 to plus infinity. But if we, for instance, interpret log of 1 plus x, as is often the case, as a utility that derives from consumption of a given quantity of a good, the quantity is x, it doesn't make sense to consider negative consumption, only no consumption at all, or positive consumption. And in this case, we could impose x greater or equal to 0 to our domain. Okay, so this is our choice. This just means that the function is not interesting in the other part of its natural domain. The graph of a one variable function is not just a picture in the plane. It has a mathematical definition. The graph of a one variable function is a set of points. I mean, you input into the function value x, and you get value y. So you have a pair, an ordered list of 2 elements, x, y. Then you do the same with another value for x, and you have another pair, and so on and so forth. So these are points of the Cartesian plane. You plot all the points. So you consider the set of all the points in the Cartesian plane. The Cartesian plane is called R squared. R is the real line. Okay, the set of real numbers. R squared, which is the Cartesian product between R and R, is the set of all possible points in the plane, in the Cartesian plane, okay? So the graph is a set of points in the Cartesian plane, the coordinates of which are pairs of input-output values for f. Or more formally, is the set of points x, y that belong to R squared, such that y is equal to f of x for any x that belongs to its domain. And this is the formal definition. Just remember that this, I mean, if we try to be, this is not the main goal of this course, but if we try to be a little more general, then it is quite often basic definitions for one variable functions carry very naturally to multivariable functions, okay? In this case, we have a very similar definition. What is a graph of an n variable function? Okay, in the two variable case, we have a curve in the plane, so the geometric intuition is very, very easy, okay? In the case of a 10 variable function, we don't have any geometric intuition on what the graph of a function is, but mathematically the definition is identical, except we have n variable instead of 2 variable. The function is defined not as a function from the set of real numbers to the set of real numbers itself, but from Rn. Rn is the set of all possible ordered lists of n real numbers. To R, because it takes values, you know, the dependent variable is always y. It is a one-dimensional variable. Is the set of points x, y. Now x is a vector, not a single variable x. Okay, it's a set of points x, y. It belongs to R n plus 1. Okay, it has n plus 1 components, such that y is equal to f of x. The definition is the same for any x that belongs to the domain. This is just an example that I show to students to show that, I mean, generalizing things is not just, I mean, something that mathematicians do to make things more difficult. It's the opposite, to make things more easy and to drive results immediately. By analogy with simpler cases. Okay. For instance, a two variable function. Here we have the geometric intuition of a two variable function. Two variable function. The graph, in this case, is a surface in the three-dimensional space. Okay, a surface in the three-dimensional space. We will see more examples of this later because it is related also to the level curves of a two variable functions, and we will see also graphical examples of this. Next, what is an increasing function and a decreasing function in one variable? I think that, I mean, what is the, okay, so how, the structure of the class with the position of the break will be like this, okay? We start at, for instance, today, 12:15, okay? Then 1 hour and a half, so we take a break at 1:45. A 15 minutes break. We start again at 2 until 2:45. The 3 academic hours are like this, okay? I think this is reasonable. Okay, so what is the concept of increasing or decreasing functions? Take a function. Suppose, as is usual in many definitions in mathematics, that this function is defined over an open interval. So it's usually very convenient to leave the boundary of the interval outside the definition and possibly to consider them apart as a special case later, okay? So when we give definitions, usually we suppose that a function is defined on an open interval. And take any, not just a specific choice, any 2 points, x1, x2, in this interval. So for instance, this is a function. It's defined in an open interval from a to b. Take 2 points, x1, x2, or x prime 1, x prime 2. Okay. Any 2 points. And take these points such that, without loss of generality, such that x2 is larger than x1. So take x2 on the right of x1. Otherwise, you can rename them. Okay. If it happens that also f of x2 is larger than f of x1, okay, or equal to f of x1, then we say that the function f is increasing in this interval. When we say that the function is increasing, usually we mean that it is weakly increasing. So also equal can hold here. If we have the same definition but equal is excluded, that is, if f of x2 is larger than f of x1, then we say that the function is strictly increasing over this interval. I mean, f of x2 larger than f of x1 for any choice of x1, x2 in the interval, for any choice, such that x2 is on the right of x1, okay? For any 2 points, x1, x2. Symmetrically, we have that if f of x2 is less or equal to f of x1, we have a decreasing function over the interval. If the inequality is the same but holds strictly, we have a strictly increasing function in the interval, okay? So these are immediate, intuitive definitions, but I want to show you just an example here. It's qualitative. Qualitative in the sense that I represented a function here which is supposed to be constant in this central interval, okay? It is possible to construct these functions. It increases here, then very smoothly, here, very smoothly, with no corners, it becomes flat here. And then very smoothly, it starts again to increase here, okay? This function, if I consider this over interval AB, it is increasing, though not strictly increasing, okay? Because if I take the 2 points, the purple ones, x prime 1 and x prime 2, with this x2 larger than x1, okay? And I look at f of x prime 1, it is here. F of x prime 2, it is here, and f of x prime 2 is strictly greater than f of x prime 1. But this is only one of all the possible choices of x1, x2. If I take x1 and x2 here, what happens? That the values of f are equal to each other, okay? And this means that it is not possible, I mean, it is increasing, but since it is not possible to find, it is not possible that since not for any possible choice of x1, x2 we have this property, but sometimes there is an equal sign, this is weakly increasing, which means increasing, just increasing without strictly. Okay, so I hope this is enough. How do we prove that a function is increasing or decreasing on an interval? This is another example that I show to students to show that we have definition. Definitions in mathematics are necessary to properly define quantities, okay? Concepts, objects. But not very often they are also useful from an operational viewpoint. So in general, we don't use definitions, the definition of increasing function, to prove that a function is increasing, unless in very simple cases. In most cases, what we do, and this is a common path, research path in mathematics, what we do in most cases is, okay, we have increasing functions, try to characterize them, to see whether they have some other properties that characterize them and only them. But this property is something more useful from an operational viewpoint, okay? Which is, in the case of mathematics, increasing functions, provided that they are smooth, have a non-negative derivative, okay? And then to prove that a function is increasing, we use the sign of the derivative, okay? But in principle, we can, in some cases, also rely on the definition. The function y is equal to x to the power of 3 plus 1, which is represented here, is a strictly increasing function, okay? Can we prove it by the definition? Yes, we can, because take x2, of course, this is defined for any real number. Very easy. Take x2 larger than x1. Try to see what happens in general to f of x2 and f of x1. Since the exponent is 3, if we have this inequality and we raise both terms to the power 3, what we obtain preserves the original inequality, okay? This is elementary algebra. If x2 is larger than x1, then x2 to the power of 3 is larger than x1 to the power of 3. Take x1 and x2 positive, negative, 0, whatever. This holds. Then if I add 1 to both sides, the sign of the inequality is preserved. So this also holds. But this is f of x2, and this is f of x1. So I have proved by the definition this situation. If x2 is larger than x1, for any x1, x2, then f of x2 is also larger than f of x1. So my function is strictly increasing over the interval. Okay? So this is just an example to show you that definitions are useful to define properly defined quantities and objects and properties, but not always useful to prove that something, to prove that these objects are as specified by the definition. We do that with other properties that are characterizing properties of these concepts. For instance, for differentiable functions, strictly increasing functions have a derivative which is positive or zero. For instance, in this case, for those who already know something about calculus, this is strictly increasing, but it happens that the derivative at zero is exactly equal to zero. So, not just positive, okay? It's positive, the slope is positive, but here the slope is flat. Anyway, we will come back to this example later. Okay, so, very quickly, straight line, linear function. You all remember, it is so popular that I guess that also the equation has the same letters here. M for the slope and Q for the intercept. Y is equal to f of x is equal to mx plus q. M is called the slope, Q is called the intercept. By the way, this is the explicit form of our linear function. We have also an implicit form for the linear function, which is written in this way. In all cases, except one, from the implicit form, we can derive an equivalent explicit form. But there is one case, which is precisely the case where b is equal to 0, in which we cannot derive an explicit form. And this means that the equation of the straight line in implicit form defines a function in all cases except when b is equal to 0. Okay? Why? Because you can start from this one. You can move to the right c and ax and divide by b, and you get y is equal to minus a over bx minus c over b, and the structure is the same as this one. It's enough that you rename minus a over b as m and minus c over b as q. You have the same structure as this one. But if b is different from 0, you cannot divide by b. So you cannot obtain the explicit form. In fact, in this case, you don't have any function, but you do have a straight line. It is a vertical straight line. Okay? If b is equal to 0, we have the straight line of equation x is equal to minus c over a, which is a straight line, but it is not a linear function because it is not a function. Okay? Is that clear? Okay. Another important thing about functions, about linear function, is the meaning of the slope, which is very useful for applications. Intuitively, when we have a linear function like this, we can say very intuitively and roughly, in a sense, we can say that it has the slope of this curve doesn't change if you change the variable x. Okay? It is always the same slope. How can we make this concept more rigorous? The slope is just the change in the value of y when x changes by 1 unit. And it is independent on the initial value of x. Okay? If you start from x and then take x plus 1, the change in y is f of x plus 1 minus f of x. F of x plus 1 is m times x plus 1 plus q. Okay, I just replaced here as the variable x plus 1. F of x is m times x plus q. If you compute the difference here, everything disappears except m. And this means that m represents the change in value of y when x changes by 1 unit. More generally, you don't even need that x changes by 1 unit. The change of x can be any change, okay? The change of x is not 1 unit, it is x2 minus x1. It is this interval, is the change of x. Put this in the denominator. What is the corresponding change of y? It's y2 minus y1. Put this in the denominator. Take the ratio, and you see that the ratio is always equal to m. The exercise is similar to this one. You can do that if you like, but the change, the ratio between the changes, the vertical change and the horizontal change, is always equal to m. This is the meaning of having the same slope, always the same slope. Two useful formulas among the many formulas about the straight line. One is, because these are useful for linear approximations in calculus, okay? So we need them to compute, for instance, linear approximations, tangent lines, differentials, and so on and so forth. The first formula, they are basically the same formula, because m is equal to this quantity, okay? In one I use m, in the other one I use this. A straight line passing through a given point, so this is data for our problem, and with the given slope m, which is also data for our problem. What is the equation of the straight line? Okay, since m is equal to, from this, y minus y1 over x minus x1, and we know x1 and y1, we can multiply both sides by x minus x1, and we obtain this. Okay, just put x1, y1, and m in your equation, and you get the equation of the straight line. This is the first formula. If instead of using m, you compute m from 2 points, having coordinates x1, y1, x2, y2, you have basically the same formula, but you can compute a straight line through 2 different points. The straight line, look at this second part of the slide. Straight line passing through x1, y1 and x2, y2. Okay, the slope is this one. This is the previous formula. I replace the slope m with this, and I can, these are all data of our problem, and I obtain a linear expression that relates y and x. Okay? Here are 2 examples which may be useful. Suppose that I want to compute the equation of the straight line passing through point x1, y1, point minus 1, 2, here, minus 1, 2, this green point, and having a slope equal to minus 1/2. What is the meaning of slope minus 1/2? If x increases by 1 unit, y decreases by 0.5 units. Okay? Put them into the equation. Y minus 2, y minus y1 is equal to m, slope, times x minus x1, that is times x plus 1. Rearrange the terms and you get y is equal to minus 1/2 x plus 3 over 2. In this way we have written the straight line emphasizing the slope and the intercept. 3 over 2 is the intercept. Without imposing m minus 1/2, but leaving this m variable here, we would get all the possible straight lines passing through this point, which is a set of lines centered at a given point. If we also impose the slope, of course we select just one among these straight lines, which is precisely the blue, the brown one. Okay, so the green one is the set of lines, straight lines through the point. The brown one is the one among them having slope equal to minus 1/2. Another example for property 2. I have 2 points now, x1, y1, x2, y2. I compute first of all the slope. Okay, so it is y2 minus y1 1 minus 2 over x2 minus x1, 2 plus 1, and this becomes minus 1/3. And then I use any of these 2 points. I use, in this case, x1, y1. I can use any of these 2 points. I have the slope here. I use the formula 1, okay? And I obtain the equation of the straight line. This is the equation of the straight line in explicit form, or if you like, this is the equation of the same straight line in implicit form. Okay, let me just show you a couple of things about explicit and implicit forms. This is something that is not really useful now, but it is useful when we will deal with implicit functions, okay? I'll just remember this, minus 1/3 x plus 5 over 3. Okay, this is the equation of the previous straight line in explicit form. If I multiply both sides by 3, I obtain 3y is equal to minus x plus 5. Or I can write x. Sorry. You can see. Oh, yeah, sure. Let me, okay. Okay, so we have x plus 3y minus 5, right, equal to 0. Look at this structure. This is something of the type capital F of 2 variables, x, y, which means a function of 2 variables, an expression that depends on 2 variables. The left-hand side is an expression that depends on 2 variables, equal to 0, okay? Instead, here we have y is equal to f of x. But y equal to f of x can be written also as y minus f of x equal to 0, right? So this is, in general, something that we can call like this, f of xy, capital F of xy, an expression that depends on 2 variables, okay? Sometimes functions are defined explicitly in this way. This is the case of the straight line, of course, but more general functions. Y is equal to something that depends only on x. And this is called explicit form of a function. For instance, y is equal to the square root of x minus 16. Okay? Sometimes functions are expressed in this way. This is the example of the straight line. X plus 3y minus 5 equal to 0. More generally, you get f of xy equal to 0, an expression that depends on x and y equal to 0. The point is that in general, when you have an expression like this, you have a curve in the plane that can be a function or cannot be a function. So there are some expressions, for instance, x squared plus xy plus y squared, depends on x and y, that not always are functions, but are just curves in the plane, okay? These sometimes are not functions, sometimes are functions, most often they are functions, sometimes they are not. But if you can just write a function in this way, this is of course a function, because for any value for x, you can only compute one value for y, okay? When these are functions, for instance, this could be the case, these are called implicit functions. This is a different concept from being able to solve the equation for y. I mean, we may not even be able to solve from the algebraic viewpoint y equal to something that depends on x. Because it may be impossible from an algebraic viewpoint. But there are tools to understand whether they are functions or they are not, and also to compute the slope of these functions. Okay? This is called the theory of implicit functions. Of course, we don't need the theory of implicit functions for the case of the straight line, just because we can just write it in explicit form. Okay? But in some cases, we cannot write this in explicit form, but this may be a function, or we can write this in explicit form, but it is not that convenient to write it in explicit form, because the expression can be very complicated. So it may be possible or just convenient to study the implicit form of the function. And this is called the theory of implicit functions. We will say something about that, and in particular we will be able to compute the derivatives of implicit functions. Okay? So this clarifies why I wasted some time on the straight line and implicit and explicit function. What about the linear inequalities? The linear inequalities are not linear equations, so they are not straight lines, but they are strongly related to the equation of a straight line. So x plus 2y minus 8 equal to 0 would be the implicit equation of a straight line. X plus 2y minus 8 less or equal to 0 is not an equation. It is an inequality, but it is related to the corresponding straight line. This doesn't represent a straight line in the plane. This represents a half plane that lies below or above. It depends on the sign of the inequality. In this case, it lies below the corresponding straight line. Okay? So basically, if we want to represent these linear inequalities, we have to look at the corresponding straight line, if possibly write the straight line in explicit form, but it is often more convenient to leave it in implicit form, understand graphically the behavior of the straight line. For instance, in this case, the most natural way to represent the straight line is to look at the intersection with the x-axis and the y-axis. Intersection with the x-axis as y equal to 0. So if you put y equal to 0 here, you see x equal to 8. And this means that our straight line intersects the x-axis at the point 8, 0. If you want to compute the intersection with the y-axis, remember that the y-axis has equation x equal to 0. Okay? So put x equal to 0 here, and you get y equal to 4. Once you have 2 points, and these are the easiest point to compute, you have your straight line. Okay? But next, along the straight line, we have the equal sign. We are interested in the less or equal sign here. And in this case, we are below the half plane, below our straight line. Is the solution, graphical solution to this inequality. Why is that? Because if you're not sure, I mean, it can be the upper half plane or the lower half plane, okay? Just check with one point. The easiest point to check is 0, 0. Put 0 and 0 here, which is the origin. You get minus 8 less or equal to 0. This is true. So this 0, 0 point satisfies this inequality, and all the points of the half plane, including the origin, satisfy the inequality. This is the easiest way to check which of the two half planes satisfies the inequality. Okay, so I hope this is clear enough. A typical example in microeconomics, and you all know this example, is the budget constraint and the budget set. Okay. We have a straight line here, which has equation P1x1 plus P2x2 minus M. M is not the slope. M is the monthly budget, for instance, less or equal to 0. Or P1x1 plus P2x2 less or equal to M. M is the monthly budget. P1 is the unit price of good 1. P2 is the unit price of good 2. X1 is a quantity consumed of good 1. X2 is a quantity consumed of good 2. The left-hand side is the monthly expenditure, the planned monthly expenditure. The right-hand side is the budget, and it's very natural that this inequality must hold if you don't want to resort to debt, for instance. It is common to impose this inequality. And then, since these are quantity consumed, also this inequality must be imposed, x1 non-negative, x2 non-negative, and all of these three inequalities must hold together. We already know that the first inequality is satisfied in the half plane below the corresponding straight line. But then this implies that you must be on the right of the vertical axis, and this implies that you must be above the horizontal axis. So you take the intersections of all the half planes defined by these inequalities, and you get this triangle, which is called the budget set, okay, for the consumer. This is an example in which we use parameters to define a straight line, and we can also find, for instance, the intersection points as functions of the parameters with a very clear meaning. The intersection point here is just the budget divided by the unit price 1, and this is the budget divided by the unit price 2. Okay, I think that we can stop for a while, for about 15 minutes. Then I will show you quadratic functions, and maybe we have the slides on the website. And I will show you also how to play with the Desmos software, or just as an example to see what happens when we change the parameters of the quadratic function. Okay. Okay, so we stop for about 15 minutes. We're back in 15 minutes.